And it's time for video lesson number 7, the nature of liquids. So we're moving away from gases and getting into the physical state of liquids. And the key question is, what factors determine the physical properties of liquids? Well, one of the things that we know about liquids is that they flow. Substances that can flow are referred to as fluids, which include gases and liquids. Gases can flow because they move in a straight line motion, then we can actually show that, and I will demonstrate that in class. But it also allows them to conform to the shape of their containers because they are able to flow. Gases and liquids have a key difference between them, however. According to the kinetic molecular theory, there are no attractions between the particles in a gas. The particles in a liquid, however, are attracted to each other because of their intermolecular forces. The intermolecular attractions keep the liquid particles close together and is why the liquids have a definite volume. Liquids are much more dense than gases, however, because they do occupy a smaller volume with the same amount. If you have the same number of particles but smaller volume, the density is going to be greater. So increasing the pressure on a liquid hardly affects its volume at all because it occupies a small amount of space to begin with. And the same is true for solids. And because you can't really compress the liquids and solids, they're known as condensed states of matter. Another key question is, what is the relationship between evaporation and kinetic energy? The conversion of a liquid to a gas or a vapor is called vaporization. It's the process of evaporation. When this conversion occurs at the surface of a liquid that is not boiling, the process is called evaporation. So if you just had some water in a glass and the water just evaporates, you're not boiling it, it's just sitting there, and over time it evaporates. That's the process of evaporation. The process of evaporation has two different outcomes depending or not if you have it in an open system like a lake or an open container, or if it's in a closed system like in a sealed container. So in an open system, the molecules evaporate and can escape from the system, as we see in this open container. The gas molecules, they're going to leave the surface of the liquid and go up and out of the container. In a closed system, the molecules collect as a vapor above the surface of the liquid. So if this is the liquid down here, these particles have escaped, have gone into the vapor phase, and they can, as they're moving around, they can collide against the surface of the liquid and actually go back into the liquid state. So they kind of go into the gassy state and back into the liquid and go back and forth until you kind of reach an equilibrium. During evaporation, molecules have to have a certain minimum kinetic energy. They have to have a certain amount of speed in order to escape from the surface of the liquid. If it doesn't have that minimum amount of energy, then they're not going to leave the surface of the liquid. They're going to stay in the liquid state. Some of the particles that do escape collide with the molecules in the air and rebound back into the liquids. They go back and forth between the gaseous and liquid state. A liquid evaporates faster when it's heated. And why is that? Well, it's because the liquid increases the average kinetic, heating the liquid increases the average kinetic energy of the particles. The added energy allows the particles to overcome those intermolecular forces that keeps them in the liquid state, and then they're able to leave then the surface of the liquid. It's all about those intermolecular forces. As the evaporation occurs, the particles with the highest kinetic energy tend to escape first. So if we kind of look at this diagram that we have here, these particles here, these are the particles that have left the surface, and we see it's water, have left the surface of the water. Well, these are the particles that have the higher kinetic energy than those that remain in the liquid. Now, what happens is the particles that are left, so these are the particles with higher kinetic energy. So these particles that are left, they actually have a lower average kinetic energy than these particles that have escaped. And so as the evaporation takes place, the liquid's temperature decreases. So that kind of sounds kind of weird, because evaporation is actually a cooling process. So these particles with higher kinetic energy leave. These particles left have a lower average kinetic energy. Well, if you have a lower kinetic energy, you have a lower temperature. Pretty cool, huh? So, like I said, evaporation is actually a cooling process. So think about this. Why do we perspire? Well, when you perspire, water molecules in your perspiration absorb the heat from your body. They're moving faster. Those ones on the surface, they evaporate from the skin, and so the water molecules left in the perspiration actually are at a lower kinetic energy, a lower temperature. So this evaporation leaves the remaining perspiration cooler. And that's why we perspire, to actually cool our bodies down. When can a dynamic equilibrium exist between a liquid and its vapor? Well, what is a dynamic equilibrium? A dynamic equilibrium is when the forward reaction equalizes out with the backwards reaction. So if we're looking at the liquid and the gaseous state, a dynamic equilibrium would be when you have equal number of particles going back and forth between the liquid and the gaseous phases of matter during that process of evaporation. So if you had a partially filled container of a liquid, okay, and it's sealed, some of the particles at the surface of the liquid are going to vaporize. They're going to go into the gaseous phase. Those particles collide with the walls of the sealed container. And remember, collisions produces pressure. So those gas particles that are above the liquid is causing pressure in the container. A measure of the force exerted by a gas above the liquid is called vapor pressure. All right, so that's a vapor pressure. And let's kind of draw a picture of that. So if we have, our container, all right, it's a sealed container, and we have liquid here. Well, we have particles that are going to escape the liquid, and they're going to bounce off, collide with the sides of the container. This is what's creating a pressure, and that's the vapor pressure of our container. So over time, the number of particles entering the vapor phase increases, and some of the particles condense and return to the liquid state. And so what we see here, we have some of the liquid going into the gaseous state, and then some of the gas are going to condense back into the liquid state. And when this process goes on, eventually the number of particles condensing will equal the number of particles vaporizing, and that is what is called a dynamic equilibrium. Okay, and they kind of balance one another out. Another key question is, in a system at constant vapor pressure, a dynamic equilibrium exists between the vapor and the liquid. The system is in equilibrium because the rate of evaporation of the liquid equals the rate of the condensation of the vapor. At equilibrium, the particles in the system continue to evaporate and condense, but you'd have no net change of particles in the liquid or the vapor phase because they're constantly going back and forth between those two phases. That's a dynamic equilibrium. When you increase the temperature of a contained liquid, this increases the vapor pressure. And so why is that? Think about that. So the particles are you increase the temperature, they're going to increase their kinetic energy, as they increase their kinetic energy, then you have more particles going into the vapor phase. And as you have more particles escaping from the surface of the liquid going into the vapor phase, then you have more collisions on the side of the container, and that increases the vapor pressure. Vapor pressure tells us how volatile a given liquid is. And when we look at this volatility, when we say something is volatile, we're looking at how easily it's able to vaporize, how easily it's able to evaporate. And so the higher this number is, the more volatile that substance is. So let's take a look at 0 degrees Celsius. At 0 degrees Celsius, the vapor pressure of diethyl ether is 24.7 kPa compared to water at 0 degrees Celsius is 0.61. So the higher that vapor pressure is, the more volatile, the more easily that substance is able to evaporate. Vapor pressure of a liquid can be determined with a device that's called a manometer. And so what you have here, okay, if we take a look at, where's my little pointer thing? Okay, if we take a look at this flask here, this flask we fill up with, we can fill it up with a liquid like we have here with the ethanol. Okay, and then you have glass tubing that connects to it. You have a U-tube, and in the U-tube you have mercury. So you have air particles that are pressing down on this side. That's the atmospheric pressure. And then you have gas particles, okay, that have evaporated from the surface of this liquid that comes down and presses on the mercury on this side. And so you have these gas particles coming up. They're going to press down the mercury. And so we see, and this is an open tube. It's open to the air. And so we measure the difference between the heights of the mercury at this end and this end, and then this tells us what the vapor pressure is. Now notice this is at 0 degrees Celsius. So if we heat this up at room temperature, notice you have more particles. Gas particles are evaporating. So you have more particles that are pressing down on the mercury on this side. So it presses down on this side, pushes the mercury up on this side, and so we measure the distance between the two levels of the mercury, and that gives us the vapor pressure of the ethanol at room temperature. And that's a manometer, and that's how we measure the vapor pressure of a liquid. And so that, my friends, ends this video lesson. And so once again, I'm going to ask you to have fun, be happy, and dance. This is Mrs. Wheathy. So long for now.